Hello everyone. In this video we're going to learn how to solve trigonometric equations, and this is part one of a two-part series. In this video we'll look at equations containing trigonometric expressions with simple arguments that only have a coefficient of 1. In the next video we'll look at problems involving other types of coefficients. We're going to start this video with first reviewing some of the algebraic skills that are going to be required to solve these trigonometric equations. Let's go ahead and take a look at one simple linear equation. For linear equations, the approach is very simple. We get all our variables on one side, the constants on the other side, then we'll solve for the variable. But if there is any simplification to be done on either side, we'll do that first before we proceed. In this case, there is no simplification possible on either side, so we'll go ahead and separate the variables. We will go ahead and move the variables to the left side. So we get 3x plus 5x equals, and we'll move the negative 5 to the other side to become 4 plus 5. And so now we have 8x equals 9. Dividing both sides by 8 will give us x equals 9 over 8. And that's about as simple as an equation as we can get. Sometimes trigonometric equations will have sines and cosines with them, but the actual algebraic part involved will be as simple as this, or even simpler. Next, we're going to look at a quadratic equation. The approach for quadratic equations is different. We move all terms to one side and have 0 on the other side so that we can factor and then apply the zero factor property. If factoring is not possible, we can always utilize the method of completing the square or the quadratic formula. But for most problems in a trigonometry class, factoring is usually possible. So let's see if we can go ahead and factor the left side. As you recall, we basically need two expressions here whose product is x squared. We need 2 here whose product is -2, and then the inner product and the outer product will need to add up to the middle term. So this seems to be a fairly straightforward one. We can get x and x here, and then I would think +2 and -1 should take care of business, because we have now x times x is x squared, -1 times 2 is -2, and -x plus 2x gives us +x, which is what we would hope for. Now we go ahead and apply the so-called zero factor property, which basically says if a times b is equal to 0, that implies that either a is 0 or b is 0. And of course, when we say or in mathematics in that sense, we say it in an inclusive sense, meaning this or that or both. All right, so now we go ahead and set each of those factors, x minus 1 playing the role of a, x plus 2 playing the role of b. So we set each factor equal to 0, and we end up with x equals 1 or x equals -2. All right, and that basically solves that particular equation. Here's another quadratic in disguise, because it doesn't seem that way yet, but once we distribute it, we end up with x squared plus 3x equals 1. Now notice that with this equation, the method of factoring does not seem possible, so just for review purposes, we will go ahead and apply the quadratic formula here. So we know that we have x equals -b plus or minus square root of b squared minus 4ac over 2a. Anytime that you want to use a formula in mathematics, write it down in its original form, then do your substitutions to minimize the chances of making an error. In this problem, we can see that a equals 1, b equals 3, and c equals -1. So if we go ahead and substitute, we get negative b, which is the opposite of b, so -3, plus or minus square root of b squared, so that'll be 3 squared, minus 4 times a, which is 1, times c, which is -1. Now we divide all that by 2 times a, which is 2 times 1. So we end up with -3 plus or minus square root of 9 plus 4. So we write that over 2. So we end up with -3 plus or minus square root of 13 over 2. That actually constitutes two solutions. The solution set includes the negative case, which is -3 minus square root of 13 over 2, as well as the positive case, which is -3 plus square root of 13 over 2. So that's how you handle a quadratic situation where factoring is not possible. You could try to factor that and you'll realize very soon that that is not factorable. In case you're interested, there is a quick way to check to see if a problem like that is factorable or not when the coefficients are integers, and we have a expression called the discriminant, which is b squared minus 4ac. If you calculate that here, you'll get 3 squared minus 4 times 1 times -1, which is 9 plus 4, which is 13, as we have already calculated. When this is not a perfect square, this expression will not be factorable. So that's a quick check in case you are interested. All right, here we have one more quadratic to look at. This time we're going to square this side, so we have to be very careful to realize that when you have a first item plus a last item squared, that is not going to be f squared plus l squared. The correct formula is f plus l, quantity f plus l squared equals f squared plus 2fl plus l squared. So now here f is being played by x, and L is being played by square root of 3. So basically we get, no equal sign in the beginning of an equation, we get x squared plus 2 times x times radical 3 plus square root of 3 squared equals 1 plus x squared. Now, the nice thing that we notice here very quickly is that these x squares can cancel out. Whenever you have the exact same term as far as the expression and the signs, they have to be the same. You can always cancel them because you just add the opposite to both sides. So we're left with 2 radical 3x plus 3 equals 1. So we get 2 radical 3x equals 1 minus 3. So we end up with 2 radical 3x equals -2. Dividing both sides by 2 radical 3 will give us x. So we get x is equal to, we notice here that the 2's here will cancel out. So we basically get -1 over radical 3. Now we can go ahead and rationalize. We always want to rationalize the denominators before we enter the answer. For that, we're going to go ahead and multiply by square root of 3 on the numerator and the denominator. So finally we end up with x equals negative square root of 3 over 3. And that's how you handle one of those. All right, let's look at one last problem before we move on to trigonometric equations. All right, so this is the situation where normally we handle with what's called the square root property, which indicates that if x squared is equal to a constant, then x must be plus or minus square root of the constant. Of course, it's easy to see why that's true, because when you take the positive square root of k and square it, you get k. And when you take the negative square root of k and square it, you also get k. So this can always be utilized when there is no x term. There's only a square term and a constant. So we notice here that we get x squared equals negative 7. So x equals plus or minus square root of negative 7. Now, from an algebraic point of view, that's a perfectly good solution. We can actually write it as plus or minus square root of 7 times square root of negative 1. So we get x equals plus or minus square root of 7i. But in trigonometric situations, we're only going to be dealing with real numbers. So in this kind of a situation, it's not going to end up giving us any solutions. So, but I just wanted you to see that so you're familiar with it if we encounter it. All right, now we want to go ahead and take a look at an actual trigonometric equation. And here we're asked to solve this equation over this period for x values in this zone, which starts here at 0, goes all the way around the circle, but stops just short of coming back to 0. Because notice 2 pi is not included. So we basically want to look for solutions by going around the circle once. We're going on a hunt is what we're doing. All right, so we have 8 sine x. Notice this will be handled like a linear equation because there's no square of sine or any other trig function. So we go ahead and go like this. So we end up with 8 sine x equals 4. So we end up with sine x equals 4 over 8, or sine x equals 1/2. So basically, we are going around the circle and we're looking for any values of angles whose sine is 1/2. If you recall, sine is the y value. So we don't have to go far to get to the first one. We can see that pi over 6 is exactly such a radian measure. And but it's not the only one, obviously, because we know that y values are also positive in the second quadrant. So this close relative of pi over 6 is also going to be one of our solutions. And if they're giving us the area to look in terms of pi, you're going to go ahead and give your answers in radians. All right, so here, notice that we're going to get 2 solutions. Of course, these other relatives of pi over 6 will not work because for those two, the sign is negative 1/2. So we're going to say that x can be either pi over 6 or 5 pi over 6. And that's it. That's all we have to do. All right. So make sure you can do a simple problem like that before we proceed. All right, so here we have another equation to look at. and we're also solving over the same period. So here we want to know sine squared x. We're going to isolate it. Remember, this is a square root property type like we just saw. And of course here there is no x value for which the sine is going to be once squared give us -1. So therefore here this is a situation where we say there is no solution. Because if you take the sine of any angle, remember sines are just y values, right? So not just even the ones for just the nice values associated with 30, 60, 90 or 45, 45, 90. For any angle, it could be a very irrational number as far as the number of radians you go around, but still it's going to be some number between 0 and 1. So it's never going to, once squared, give us a negative answer. So basically we write the solution set is empty. We can use the null set notation here, or we can just put these braces and not put anything inside it. They mean the same thing. They both mean the empty set. All right, so here it looks like we have a quadratic situation because there's a square term, a first degree term, and a constant. So this should be of the type ax squared plus bx plus c equals 0. So we're going to go ahead and get every term on one side and make sure we have 0 on the other side. So in other words, of course, 0 is a term too. So we mean all the non-zero terms on one side. All right, so we get 2 sine squared x plus 4 sine x plus 2 equals 0. We move the -2 to the left side. Now we notice here that we have a common factor of 2 in all terms, and we never lose an opportunity to make life simpler. It's difficult enough as it is, right? So we'll go ahead and divide both sides by 2, and then it splits up on this side. So basically each of those gets divided by 2. So when we simplify that, we end up with sine squared x plus 2 sine x plus 1 equals 0. So now we're going to go ahead and factor this just like we did with the algebraic review, and except now we want two expressions here and here whose product is sine squared x. So obviously we can use sine x and sine x, and we want two numbers here whose product is 1. So that should be simple enough, right? And there's positive signs all around, so we would think it'd be positive. The last thing we want to check, make sure the inner product, which is sine x, and the outer product, which is also sine x, add up to 2 sine x, and they do. So we have the correct factorization. Now we go ahead and apply the zero factor property. So since a product of two expressions is 0, one or both must be 0. So we go ahead and set each one equal to 0. Now, if you notice, this actually turned out to be a perfect square trinomial because both of these are the same. We really didn't need to write it twice, but we did just for the sake of displaying that the root that we're going to get is going to be what's considered to be a double root, because it will become a root of this solution twice. So we get sine x equals -1. Obviously we don't need to solve both of those, they're the same equation. So now we're going around the circle and we're looking for a radian measure so that the sign of that radian measure or that real number is -1. And of course, remember that sine is the y value. So when we start going around the circle, we see that the only place from 0 to 2 pi where the y value or the sign of the angle is -1 is right here at 3 pi over 2. So we get x equals 3 pi over 2. Of course, if they wanted the answer in degrees, we could have handled that too. We would have just said 270 degrees. Same business, no difference. All right, so simple, but make sure you can handle it, and we'll proceed to another one. All right, so here we have a product that seems to be in factored form already. So it's actually ready for a quick application of the zero factor property. So we go ahead and set each of those factors equal to 0. So the first one gives us cotangent of alpha equals 1. If you're more comfortable with tangent, you can always turn that into a tangent too, because the tangent of alpha is going to be the reciprocal of 1, which is of course 1. Let's go ahead and go to the other one and solve it before we decide what angles we need. So here we have 2 sine of alpha equals -1, so sine alpha equals -1/2. Once again, we're looking for solutions going once around the whole circle. So for this one, we want the tangent to be 1, and remember, tangent is the sine of alpha over the cosine of alpha. We want that to be 1. In other words, we want the sine of alpha to be the same as the cosine of alpha. In other words, we're looking for angles whose x and y coordinates are the same. Notice we have 1 right there. Be careful to avoid this because, yeah, their absolute values are the same, but they're not the same, they're opposites. The only other one that's going to work for us is going to be here, and that's as far as this particular part of the equation is concerned. The problem, I mean. So we get alpha equals, in this case, we're going to say pi over 4, and the one that we have here, as we know, that's 5 pi over 4. Now, obviously, if you don't have the unit circle in front of you, you can easily see what this is. You just start here, you go, that's 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, so that must be what? 5 pi over 4. It's really easy to get to. All right, so for this one, remember we have to solve this equation as well. We're looking for angles going once around the circle whose sine, basically the y coordinate of the point of intersection of the terminal side of the angle with the circle. We want that to be -1/2. And of course, we're not going to be looking up here, are we? Because up here, the y values are positive. So we're only going to look down here. And down here, the ones whose y values are -1/2 are going to be 7 pi over 6 and later 11 pi over 6. So all right, if we want to present our answers in a professional manner, we'll go ahead and put them in a solution set. So we're going to have pi over 4, 5 pi over 4, 7 pi over 6, and 11 pi over 6. Now, had they requested these in degree measure, we could have easily done that too. So pi over 4, of course, we know is 45 degrees. For the other ones, we can quickly use a calculator if we want to save time. So, for example, we know that we want let's see, we want 5 times 180 over 4 to go ahead and convert that to degrees. So 180, and then we're going to divide by 4. Okay, I think that's, I see what happened here. This calculator is a little touchy. I have to put times. Some calculators automatically assume the multiplication, some don't when there's parentheses involved, but this one really wants you to be in good proper format. All right, so 5 times 180 divided by 4, and we end up with 225. So basically, let me move this calculator out of the way. So 45 degrees, and then this calculator likes to go back to where it is. Okay, so 225 degrees, and then 7 pi over 6. So we're going to calculate 7 times, we don't forget the times this time, pi, well, instead of pi, we're going to put 180. If there's a pi in the expression, the quickest way to convert it to radian, to degree mode, is to go ahead and replace the pi with 180. Otherwise, if there is no pi in the radian measure that you're trying to convert to degrees, then you simply multiply by 180 over pi. So we get 315 degrees. 7 pi over 6, correct that, that should be a 6. So we end up with, let's see, this is not cooperating with me. We bring that back down, and we're going to go, let's see, here, and we're going to change that to 6. All right, so we get 210 degrees. These do not have to be in order. Sets are not ordered. It's nice to put them in order, but they don't have to be. And finally, we have 11 pi over 6. So I can actually cheat a little bit here, and that's one of the nice things about these advanced calculators. So we get 11 pi over 6, which is 330. So had they requested the answers in degree measures, we could have handled it very easily as well. All right, so that's how we handle a problem like this. Be sure you can do it on your own, and we'll go to another one. All right, so here for the first time, we have 2 different kinds of trig functions involved. So obviously, we're going to have to somehow turn those into one kind of trig expression. And of course, if we know our identities, then that becomes a simple matter. And we know that we have sine squared x plus cosine squared x equals 1, our Pythagorean identity. We know that if we divide both sides by cosine squared, we end up with sine squared over cosine squared, which is tangent squared x, plus cosine squared x over cosine squared x, which is 1, equals 1 over cosine squared, which is going to be secant squared x. So we're going to go ahead and replace the tangent squared x with secant squared x minus 1. So let's solve this for tangent squared x, and we get secant squared x minus 1. So we get secant squared x minus 1 plus 4 secant x plus 5 equals 0. We go ahead and combine like terms, which are just the constants basically here. So we're going to get secant squared x plus 4 secant x plus 4 equals 0. It looks like we have another perfect square trinomial on our hands. And if we just go ahead and factor it out quickly, we can see that that's going to be secant x plus 2 times secant x plus 2. So of course we don't need to set both equal to 0 this time. We know about that. We're just going to go ahead and set 1 equal to 0. So we get secant x equals -2. Now it's a little bit easier to work with cosines, so we'll go ahead and turn that into a cosine. So we get cosine x is of course the reciprocal of -2, which is -1/2. So this time we're working with degrees. We're going around the circle and we're going to locate the angles or the radian, well, degree measures this time, so really angles whose cosine, which is the x coordinate, is -1/2. So obviously we're not going to be looking here, are we? Because in here, as you know, in the first quadrant and fourth quadrant, cosine is positive. So we're going to be looking in the second and third quadrants for the angles whose associated x coordinate is -1/2. And as you can see, we have one here at 2 pi over 3. Well, actually we want degree measure this time only, so 120 degrees. And there is another one down here at 240 degrees. So that's how we know x equals 120 degrees or 240 degrees. To present that as the modern way of solution sets, we just put 120 degrees and 240 degrees. When you're doing a solution set like this, you don't need to write the x or anything like that, just the numerical value of the solutions. All right, so a pretty good problem. You should make sure you know how to do before we move on. All right, so here we have another equation. It seems like it's going to be a little bit more interesting than the others because we know that we have a relationship between the squares of cotangent and cosecant, but we don't have one between their first powers. So we're going to have to get ourselves some squares basically. And how do we get squares when we don't have them? Well, by squaring, right? So let's see what the relationship between the squares was first. So if we start with sine squared beta plus cosine squared beta, we know that that's 1. Now this time, instead of dividing both sides by cosine squared, we're going to go ahead and divide both sides by sine squared. So we end up with 1 plus here we get cosine squared over sine squared, which is cotangent squared, and on this side we get 1 over sine squared, which is cosecant squared. So we get 1 plus cotangent squared beta equals cosecant squared beta. So that's one of our main 3 Pythagorean identities we should know anyway, but if you forget it, you can always generate it very quickly in the way I just showed you. So if we go ahead and square both sides as is, we're going to end up with a little bit of a mess, because then we get a cotangent times cosecant. And if you look at that, that's like cosine over sine of beta times 1 over sine beta, and that just brings in sine as well, which is going to be kind of messy, so we won't do that. Instead, what we'll do is we'll go ahead and keep the cotangent beta on the left side, and we'll go ahead and move the 5 cosecant of beta to the other side to become negative. Now we'll go ahead and square both sides, and we won't run into that problem anymore. So at this point, we're going to go ahead and square both sides. Now, from the get-go, we're going to realize that when you square both sides of an equation, you're not doing a basic operation like adding, subtracting, multiplying, or dividing, which preserves the solutions. When you square both sides of an equation, just like we did with square root problems in algebra, you may end up with solutions that work for the squared equation but not for the original equation. So these become mandatory check problems. So once we're finished, we're going to have to check each one of our solutions. This is going to require some patience. So let's go ahead and square both sides. So we want to definitely remember that from the get-go. All right, so we get cotangent squared beta equals, we're going to go ahead and square that side using our rule, which is f minus l squared equals f squared minus 2fl plus l squared. F is going to be 6 and L is going to be 5 cosecant of beta. So we end up with 36 minus 2 times 5 times 6 is 60. So 60 cosecant of beta, and then plus 25 cosecant squared beta. Now we can go ahead and convert the cotangent squared from here. Notice you can solve for cotangent squared beta and you end up with cosecant squared beta minus 1. So now we're going to replace the cotangent squared beta with cosecant squared beta minus 1, and we end up with 36 minus 60 cosecant beta plus 25 cosecant squared beta, which doesn't change yet. All right, now we notice it's a quadratic, so we're going to go ahead and move all terms to one side. The right side seems to be the better side, and we'll get 0 on the left side. So we get, basically this becomes minus cosecant squared on the other side, so we end up with 24 cosecant squared beta minus 60 cosecant beta plus 1, and then another 36. So let's just go ahead and combine those and put plus 37. All right, so now we have ourselves a quadratic that doesn't look very friendly either. So we're going to go ahead and apply the quadratic formula with cosecant of beta being the variable here. So we get, you notice that A equals 24, B equals negative 60, and C equals 37. And what normally plays the role of X in the quadratic formula is actually cosecant of beta here. So we don't get X equals the quadratic formula, we get cosecant of beta equals the quadratic formula. So we get cosecant of beta equals negative B plus or minus square root of B squared minus 4AC over 2A. Of course, what I meant is on the left side of the quadratic formula, you don't get X, you get cosecant beta. I didn't mean for the quadratic formula as a whole. All right, so we end up with cosecant of beta equals negative B. B is negative 60, so the opposite of that is 60 plus or minus square root of B squared. We know if we square negative 60, we get 3600 minus 4 times A, which is 24, times C, which is 37. And then we have all of that over 2 times 24, which is 48. Now that's cosecant of beta. As you know, it's easier to work with signs on a calculator. So let's go ahead and write that as sine beta, and we end up with sine beta is basically the reciprocal of that. So we get 48 over 60 plus or minus square root of 3600 minus 4 times 24 times 37. All right, so Now we know that beta is going to be the inverse sine of all that. So let me just put ditto. We love dittos in mathematics, especially in situations like this. Okay, we should be ready for a calculator at this point. Let me go ahead and bring it up. So we're going to carefully type in, after checking that we're in degree mode, let's make sure. So yes, we're in degree mode, so we'll go ahead and quit out of that. And now we're going to type in the inverse sine, so second sine on most calculators. And now the numerator is 48, and we're gonna go divided by, now we're gonna open a parenthesis to contain the entire denominator. So we're gonna do the plus case first, so we'll say 60 plus square root, which is second squared on most calculators, and then 3600 minus 4 times 24 times 37. A lot of patience is required at this point for this calculation, and we end up with 45.8. Let's just approximate. So 45.8, or now we're going to do the minus case. So the nice thing about this kind of calculator is you can copy that. So now we'll just go change that plus between the 60 and the square root to a minus. All right, and that should do it. And we get 64.7 approximately. So instead of equal, we really should say, be real accurate and say approximately, or 64.7. And these are in degrees. Okay, it's time for the unit circle to get a point across. So let me go ahead and bring the unit circle over for a minute. All right, so it looks like we have a couple of angles, proposed angles, because remember, mandatory check. We're going to check all possible solutions at the end. But they both seem to be here in the first quadrant. And of course, remember, if you have an angle in here that has a certain y value or sign, then you have one also in this quadrant related to it. So if, for example, some angle here is beta, then this angle here is going to be 180 minus beta, correct? So let me show you in a simple example. So for example, if we have a 60-degree angle here, we know that the corresponding angle in this quadrant is just going to be 180, take away that 60, so this will be 120, right? So now, why call it 60? Why not look at a general angle beta, right? So if you have beta, this is here is going to be 180 minus beta, correct? So that's what we're talking about here. So let's go ahead and get rid of this and go back to our work. So that means each of these is going to have a corresponding angle in the second quadrant, which will also have a positive sign value. So what we'll do is we'll go ahead and bring the calculator back, and we'll go ahead and calculate 180 minus 45.8, which gives us 134.2. That's the angle in the second quadrant that should work. And then we'll do 180 minus 64.7, and that gives us 115.3 degrees. All right, so these are our proposed solutions. Now it's time to check, because remember we did something non-basic, we squared both sides, so we may have gotten solutions that don't work. Those solutions are called extraneous solutions, meaning solutions of equations other than the original. All right, so now it's going to be all calculator work. So now we're going to plug in each of these angles into the original equation and see if they satisfy it. All right, so we'll start with cotangent of beta. Of course, we know how we enter that. We don't put cotangent of beta, we put 1 over tangent of beta. Or better yet, we can put this expression, which is nicer on a calculator. We could put tangent of the angle and then to the power of -1. This is not inverse tangent, as you know. This is literally, it means 1 over tangent of beta, which is the same as cotangent beta. So we're going to be entering it in that way. So let's go ahead and get to work on that. So we're going to open parentheses, and then we're going to put, okay, let's not lose that again. All right, so we're going to put 1 over tangent of 45.8. That's the first one we'll check. Okay, I went ahead with 1 over tangent anyway. I guess old habits die hard. All right, so it doesn't matter. We could have done the to the power of -1, but this will work just as well. All right, so and then plus 5, instead of cosecant, we're going to put over sine. And then 45.8. And now we're ready to hit enter, because if we've done it correctly, in other words, hopefully we've done it correctly. That's not what I mean. I mean, if this works, if this is a solution, as soon as I hit enter, I should get 6. Let's see if we get it. And we don't. So that means right now we can go ahead and scratch that out. That was an extraneous solution. Now let's go ahead. Now the rest is actually going to be easy because we have the expression already there. So we're just going to go ahead and copy that. And now we're going to go ahead and put in the other angles. So let me put this first, because that has the same number of digits in it. It'll be easier. Then we'll put an insert and we'll put the other 2 angles in. So let's try 64.7 instead, and we're gonna do the same on this one. Change it to 64.7, and then we'll hit enter. This one worked. Now of course there's a little bit off, but that's because of the rounding. So we have one winner so far. All right, so now we're going to check the other 2. Those have 4 digits, so we'll have to do some inserting there. So let's go ahead and copy that again. So now we're going to type, instead of 64.7, we're going to put 134 point, and we're out of digits, so we need to do an insert. So that's second insert, and then we want 2. All right, so now we're ready to go ahead and change the other one as well. So remember, we're going to put in 1, 3, 4 point, and we have to put insert so we can bring in extra digit, and that's 2. All right, so we're gonna hit enter. All right, we have another winner on our hands. This one worked. And finally, this time it's going to be quick because we already have the right number of digits. So now we're going to put in 115.3 and the same on the other one. We're going to change it to 115.3 5 point, oops, the wrong one, 0.3. All right, and we have another loser. That didn't work either. So for our solution set, we're only going to accept the ones that worked, and that is basically 64.7 degrees and 134.2 degrees. All right, so this one had a little bit of everything in it, didn't it? It requires quite a bit of understanding. It's a great problem for real progress in trigonometry. So make sure that you understand all the little subtle details. I mean, the quadratic and all that, it's messy, but it's not difficult. The real part to really understand is why you have to check, number one, and that's because you're radically changing the nature of the original problem by squaring both sides. Remember, if you're doing a basic operation, adding, subtracting, multiplying, dividing, you're fine. You're not going to alter solutions. That is, of course, as long as you're doing so by constants. But when you square, that's not a basic operation. So you always have to check. Now, if you plug in these four into the squared equation, all of them will work because these are solutions for that squared version. But not all of them will work in the original problem, and that's why we have to do the check. So these two are called, once again, extraneous solutions. So we say 45.8 degrees and 115.3 degrees are extraneous, like this, solutions, which basically means they're not solutions. All right, so these are the only two that work, and we are done with that one. All right, so in this one we have something simpler, but it's different because this time we're not saying find the solutions in the interval 0 to 2 pi or 0 to 360 or anything like that. We're saying find all the solutions of this equation in radians. So that's going to require an understanding of how circular functions work. So let's take a look at just solving for cosine. So we get cosine x equals -1. That in itself is extremely simple. We know where the angles are whose cosine is -1. Remember, cosine is the x value, so we know one possible solution for this equation is pi. But remember, I can start going around the circle this way in the positive direction and get 3 pi. That works. Then I can go around the circle again to get to 5 pi. That's going to be another solution. Or I can go the other way around, right? And basically I can do any number of full circles around in either direction, in the positive direction or in the negative direction, and they're all going to have the same cosine, -1. So the way that we express that is this. We say x equals, we start with the first one that works, we know that's pi. So then we want to add full circles, right? So that means we're going to want to add multiples of 2 pi, and then how do we show that? We just bring in n. And then we just have to explain what n is. Of course, n is any integer, like that. So if you want to write the solution set, we normally go put it in this way. We say the solution set, we're going to have to put this one in set builder notation because it's not just a couple of problems or a couple of solutions we can just completely list. So we have to describe. That's why it's called set builder solution. You don't write the actual elements of the set, you describe how someone can get the elements of the set, or build the set. So here we say it's going to be all x such that x equals of the form pi plus 2 pi n such that, well, actually no more such that needed. You just put a semicolon and then you say for all n belonging to z. We already had our, this bar here means such that. I got a little carried away with my such that's here. All right, but that's how you do this kind of a problem where you want all the solutions of a particular equation. You don't just list ones in any particular interval, you do all the possible solutions. All right, that's simple enough. Let's look at another one of these. We have another one of these where we want all the solutions, and these are going to be the type where you don't want to use a calculator. These are going to have exact solutions. So let's go ahead and start looking at this. So we have 3 cosecant x minus 2 radical 3 equals 0, correct? So we are going to go ahead and solve for cosecant x. So we get 3 cosecant x equals 2 radical 3, and that tells me cosecant of x equals 2 radical 3 over 3. Of course, who wants to work with cosecant when they can work with sine, right? It's so much nicer and easier to work with. We know exactly what the values are, looking at the circle, etc. So we're going to go ahead and turn this into a sine function. So we get sine x equals, of course, the reciprocal of that. So 3 over 2 radical 3. And we're going to go ahead and rationalize that so that we can maybe recognize it. So we're going to multiply top and bottom by square root of 3. So we end up with sine x equals 3 radical 3 over 2 times 3. We've seen something very similar already today. So now we notice again that we can do some canceling. So now we look and we recognize that we have sine x equals square root of 3 over 2. So in order to write all the solutions, first we get the first ones, okay? So where do we know on the unit circle where the sine value, which is, as you know, the y coordinate, is square root of 3 over 2? We know where they are, right here and right there. And that's it, because the other ones are not going to be positive. So one of our solutions is going to be expressed, I should say one series of all solutions is going to be expressed as pi over 3 plus, of course, remember, pi over 3, then go full circle around, there's another solution again, or go full circle this way, another solution, etc. So plus 2 pi n. Some people write that as 2n pi, same thing, it doesn't make any difference. And the other set, infinite set of solutions is going to be starting here. So 2 pi over 3 plus 2 pi n. If we want to write it formally, we can say the solution set is all x such that x has the form pi over 3 plus 2 pi n, comma, 2 pi over 3 plus 2 pi n, and then you can put a semicolon and describe n. So that has to be any integer. All right, so simple, but different, so make sure you're comfortable with it before we move on. All right, so we finally arrived at our last problem for this video. So let's go ahead and get to work, see how this can be done. So we notice that we have a form that we have talked about in other videos that should always be recognized. And of course, by that I mean the form of a proportion. If you go ahead and write the right side as 1/1. And here, of course, we can cross multiply. So we get 10 x, it doesn't matter which one you put first, equals 11 minus 10 squared x. We could have put this on the left side and this one on the right side, makes no difference. All right, so it looks like we have a quadratic on our hands. Let's go ahead and move everything to one side and get 0 on the other side. So 10 squared x plus 10 x minus 11 equals 0. Looks like that may be factorable, so we get 10x minus, or probably plus 11 times 10x minus 1 equals 0. So now we're going to apply the zero factor property, which tells us either 10x plus 11 equals 0 or 10x minus 1 equals 0. Let's stick to the good habit of always checking these. First times first is first, last times last is last. The inner product is 11 tan x, the outer is negative tan x, and they add up to the middle term. So you should always check those. So we get tan x equals negative 11. Or tan x equals 1. Now this one, we know that we can do without any problems. So the only one that we're gonna have to utilize a calculator for is this one. This one is not one of those values that we can get from our special triangles. So we'll go ahead and bring in a calculator and go ahead and calculate the inverse tangent of negative 11. So we end up with negative 84.8. Now, while we could use that to write our solutions, it's usually nicer if we can write our solution sets with a positive value, just tradition. So if you notice, if you have an angle in here, negative 84.8 falls in here, which has a negative tangent. The one right across from it here, notice in this quadrant, tangent is also negative. So if we just take that and go ahead and add 180 to it, we can get a more pleasant form of the answer for our starting point. So we can say, if we round that, around 95.2. So instead of using that one, we'll use 95.2. So we'll say x equals 95.2 degrees plus, now remember, if an angle here has a certain tangent, then you're gonna have to go straight across. It's these two quadrants where you can get your negative tangents. So you're not gonna do plus 2 pi n this time. You can do better than that. You get more than that, because if you go 2 pi, you're only gonna get these ones here. So if you actually, instead of doing 2 pi n, do plus pi n, you'll catch these and all of these. So plus, well, in this case, we mean we're in degrees right now, so plus 180 degrees n. And this is going to be one set of our solutions. Now we'll go to the tan x equals 1. That one is easy. We know the first place where that happens is 45 degrees. And of course, we're going to do the same business. We're going to add half circles. because if the tangent is positive here, it's also positive across right here. So we're going to go 45 degrees plus 180 n as well. All right, so those are the solutions given in degree mode. Now to turn them into radian mode is easy enough. So we'll go ahead and take 95.2 degrees. You know what we need to do, right? You go 95.2 degrees times, you want degrees down here to cancel, and you want pi up here. So you're going to multiply by pi over 180. So 95.2 times pi is hiding here somewhere, pi over 180. All right, so we get come back approximately 1.7. So I really here should say approximately now, and I should have said approximately here too. Let's be really accurate. All right, so we go to just one decimal, 1.7 plus, of course this time, pi n. And in all the cases, we know n has to be an integer. All right, so for 45, that's much easier. We already know what it is. That's going to be exactly equal. We don't need to say approximately equal. That'll be pi over 4 plus pi n. That's it. That's how you handle these infinitely many solutions scenarios. So I hope that helps out, and make sure you practice these and be safe until our next video.